This lesson starts with a review of some key concepts and formulas to do with the concept of gravity, and then pulls in the idea of circular motion. And we look at some applications where both gravity and circular motion are at play. So the first important thing about gravity that I want to recall is gravity is a force that attracts every pair of objects in the universe. So what I mean by that is think of any two objects in the universe. They are feeling a pull towards each other through the force of gravity. Could be two things close by, like a pencil and an eraser that are sitting on your table. They feel pulled towards each other. Could be something big and something small, like the planet Earth and you. You're feeling pulled towards planet Earth right now. That's your weight. And interestingly, planet Earth is also being pulled towards you. Or we could talk about two objects that are like really far away. Say that eraser that's sitting on your desk and a piece of dust on the other side of Mars. Those two things are exerting a force on each other right now. That force may be small, but it's there. So speaking of how small or how big that force is, one of the things we might want to know about a gravitational force is exactly that, how small or how big it is. And it turns out that this strength of a gravitational force depends on two things. It depends on the masses of those two objects and on the distance between them. So we generally don't have to think that often about the gravitational forces that two random objects exert on each other. It's certainly rarely drawn in any of our free body diagrams. There's really only one time in high school physics, for the most part, that we consider the force of gravity, and that's when Earth is pulling something down. So why is that? Why do we always add a force on our free body diagram when the Earth is pulling something down, but we never bother adding a force when some object to the side is pulling that same thing sideways? Well, the reason is because in order for gravity to be big, we need mass to be big and distance to be small. If mass isn't big and if distance isn't small, gravity is just too weak of a force to be noticed and to have any real effect. So, throughout probably your entire life, there will only ever be one object that is big enough and close enough to you that its gravitational force is strong enough that you'll notice it. And that one object is planet Earth. That said, doesn't mean we don't want to calculate the force from some other objects. So let's look at that now. If we want to calculate how strong a gravitational force is, in other words, we want to know its magnitude, we use Newton's universal law of gravitation, which looks like this. The magnitude of the force of gravity between two objects is m1, m2, big G divided by r squared. Okay. So, m1 and m2 are the masses of the two objects. And that's going to be in kilograms. Big G is the universal gravitational constant. This number, there's sort of a number like this associated with a lot of the forces that exist in our universe. And we can kind of think of it as telling us how strong that force is in general compared to other forces. So for example, if we're talking about the electric force that might exist between like a positively charged object and a negatively charged object, it has a letter that goes with it as well. Instead of big G, it uses the letter K. And so the value of big G and the value of K tell us how strong gravity is compared to that electric force. Now, big G, it turns out, is a really, really small number. It is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That's another way you can write these units as well, but that way is sort of sufficient for us today. So big G is a really small number. That number K I was talking about for electrostatic forces, that's actually a really big number. It's 9 times 10 to the 9. So what that tells us is that gravity is actually a very, very weak force because its constant is a really, really small number. Now, the last thing in this formula we want to look at is R. And previously in physics, we probably would have told you that R is just the distance between the objects, kind of like I said up here. But I'll go one step further today. I'll give you a slightly more accurate, but slightly more complicated explanation of R. R is the distance between the object's centers of gravity. The distance between their centers of gravity. Now, as we've done previously in this course, we're mostly going to deal with uniform objects, so that means their center of gravity will be at their center. But this is a point I thought I would mention nonetheless. So that's Newton's universal law of gravitation. It tells us how strong the gravitational attraction is between two objects. You'll notice there's no vector hats on the top of FG here. Force is always a vector. The reason there's no vector hat on this equation is because this equation does not tell us the full part of FG. This equation only tells us the magnitude. To find the direction, we have to do that on our own. And that's fairly straightforward because we know gravity pulls on things. All right, so let's do a quick example here. Calculate the force of gravity between a 60 kilogram student and a 75 kilogram student if their centers are 0.95 meters apart. All right, so here is my 60 kilogram student. And here is my slightly bigger 75 kilogram student. And their centers of gravity, for most humans, the center of gravity is kind of near the belly button. So those are 0.95 meters apart. So that distance from there to there is 0.95 meters. Now, these two students are going to feel a force of gravity from each other. The student on the left is going to feel a force of gravity to the right. And the student on the right is going to feel a force of gravity to the left. because of Newton's third law, these two forces are equal and opposite. That's important. We often feel like the bigger object is going to pull harder than the smaller object will. That tends to be a thing people often think, but it's not the case. Because of Newton's third law, when the two objects pull on each other due to gravity, it has to be the same force. So that means that although the Earth is pulling on you right now with your weight, you are actually pulling on the Earth with the exact same amount of force. Your weight is not only how hard the Earth pulls on you, it's also how hard you pull on the Earth. All right, so let's figure out exactly how strong this Fg is. Okay, so our equation says it's going to be m1, m2, big G over r squared. Now, we got to figure out which mass is m1 and which mass is m2. Or maybe, if I'm honest, we actually don't have to figure that out. Because all I'm doing is taking those two things and multiplying them together, it doesn't matter which student I call m1 and which student I call m2, right? If this is 60 and this is 75, or if it's the other way around, it makes no difference. 60 times 75 is the same as 75 times 60, so I can just pick randomly which one I want to make m1 and which one I want to make m2. That said, there are times when it can be convenient to have some consistency here, to have a convention per se. So what I'm going to suggest is that we say, in general, when the question allows, we say M2 is the bigger of the two masses, and M1 is the smaller of the two masses. And it can be nice if everyone sort of uses that same convention, because then if we're looking at each other's work and we're trying to help each other out, it's easier for us to understand and see what we're doing. So I'm going to suggest we use that convention, but you certainly don't have to. So if M1 is the smaller mass, I'll put in 60 for M1, then 75 for M2. Big G is 6.67 times 10 to the negative 11. At this point, I'll remind you that this is a good time to get used to using that exponent button on your calculator. When you're typing in stuff in scientific notation like this, that button is not only makes your life easier, but makes you less likely to make mistakes. So that's a button on your calculator. It sometimes has two capital E's on it, or it says EXP, or it says times 10 to the power of something. Use that button when you're using scientific notation. It'll make your life way easier. Okay, and then we're going to divide this all by the distance between the two students, and that is going to be squared. Plugging that all in to a calculator, we get 3.33 times 10 to the negative 7 newtons. That is a very small force, which is what we would expect because gravity is in general a very weak force. It only becomes sort of substantial when we've got really large things that are really close, and on the scale of the universe, neither of these students can be considered to be pretty large things. And then a reminder, this force here is not only how strong the one student pulls on the other, but also how strong the second student pulls on the first. Those forces are the same in magnitude. They're equal and opposite. At this point, I want to remind you guys of something important. An important distinction to make when we're talking about the force of gravity. There are two things that we often use interchangeably in everyday life, but in physics they mean different things, and the distinction is important. These two things are mass and weight. I want you to think of mass as the amount of matter in something. So objects are made up of atoms. Those atoms have electrons and protons and neutrons. The electrons have basically no mass. The protons and neutrons all have the same mass. So if you were to just add up all the protons and neutrons in an object and get that number and then multiply it by the mass of a proton or a neutron, you would get the mass of the object. So in a way, it's really just a way of counting up how many protons and neutrons are in an object. It's the amount of matter in something. So you have a certain number of protons and neutrons inside you. We can think of that as your mass. If you were to travel to the moon, that wouldn't change. You'd still be made of the same atoms. You'd still have the same number of protons and neutrons inside you. So you would still have the same mass. This means that mass doesn't depend on location. You can't change your mass by going to a different planet or by going somewhere else on Earth. It is the amount of matter in you, and that is not going to change. This can be contrasted with weight. Weight is not the amount of matter in you. Weight is how hard gravity pulls on you. Weight is Fg. So if you take your mass and you go to the moon, gravity will pull on you there less than it does on Earth, because the moon has a lesser gravitational field than Earth does. So you can change your weight by going to a different place where the gravitational field has a different strength. So the weight does depend on location. In fact, you don't even have to leave planet Earth. If you go to the top of Mount Everest, you're actually a little bit further away from Earth up there. So I think your weight ends up being like 1% less or something like that, even though your mass would be the same. One way to kind of really sum up the difference between mass and weight pretty quickly is with this formula that you're all pretty used to seeing, I think. All right. In this formula, Fg is weight. It's how hard gravity pulls on something, and it's measured in newtons. And this m is mass. It's the amount of matter in something, and it's in kilograms. And so mass and weight, we can always kind of get from one to the other. If one changes, the other generally does too, unless we're going to a place where this is different. By changing little g, I can change my weight without changing my mass. All right, so let's look at a question here. A satellite weighs 9,000 newtons in orbit. Okay, it weighs that. So that's its weight. That's the force of gravity acting on the satellite. How much does it weigh if its mass is tripled and its orbital radius is doubled? Let's start with a quick diagram. Okay. Here's the Earth. And here's my satellite. orbiting around Earth. Now, it sounds like I'm going to take this satellite, I'm going to make a version 2. Version 2 is new and improved. The mass has been tripled, so this new satellite is going to be bigger, and the orbital radius has been doubled, so this new satellite is going to be further away from the center of the Earth. So I'll draw the new and improved satellite over here. Mass has been tripled, orbital radius has been doubled. Okay, let's label some stuff here. So, this term orbital radius is the radius of the orbit. So when we're talking about a satellite, the orbit is like the is this circular path that it follows around the Earth. So that blue dotted line is the orbit, and the orbital radius is the radius of that orbit. So you can see it's going to be this green arrow here that goes from the satellite to the center of that dotted circle. So this is for my initial satellite. So we'll call this R initial. But then I've got a radius for my new satellite. We'll call this R final. And these satellites have masses too. We'll call this mass M initial, mass of the initial satellite, and this mass we'll call M final, mass of the final satellite or the new satellite. Okay, so what I'm going to do is I've got some information on mass and on radius, and I'm interested in knowing about weight. Well, that sounds like this formula up here. Mass, radius, weight. Let's see if we can apply that down here. And I'm going to apply it twice. Once for the initial satellite, the small original one, and once for the final satellite. So for the initial satellite, my formula is Fg equals M1, M2, big G over R squared. So because I'm just looking at this initial satellite, Fg is going to be, I'm going to call it Fgi for weight of the initial satellite. M1 and M2 are going to be the two objects causing this gravitational force on the satellite. So if I'm looking at my little satellite, one of those masses is going to be the mass of the satellite itself. The other mass is going to be the mass of the Earth. Those are the two things that are pulling on each other in this case. So again, sticking with this convention that M1 is the small mass, M2 is the big mass. M1 will be the satellite, M2 will be the Earth. So M1 is going to be M initial from over here, the mass of the satellite. M2, I'll just leave it as that. It's the mass of the Earth. We know what the mass of the Earth is, so we could plug it in, but we don't have to yet. And I think this might be a bit cleaner if we don't. And then for radius, I'm going to use the radius of that initial satellite. And it's squared. Okay, so that's what's happening with my initial satellite. Now let's look at the new and improved version, my final satellite, or satellite B. Again, the same formula applies. Newton's universal law of gravitation. M1, M2, big G over R squared is the force of gravity on the satellite. But this force, this satellite over here, is going to feel a different force So I'm going to call it Fg final. And that force is due to two masses, the mass of the satellite and the mass of the Earth. Those two masses are what create that force. Again, I'll use the satellite for M1. M2, I'll just leave it as M2. That'll be the mass of the Earth. And the radius between them, the distance between their centers of gravity, is R final. Now what this question is getting me to do is it's getting me to sort of compare the weight of the new satellite with the weight of the old satellite. So I want to kind of get this expression for weight of the new satellite over here to look similar to this expression for the old satellite, so I can compare them and see how they're different. Well, one thing I notice is this new formula has mass final, whereas the old one has mass initial, and the new formula has R final, whereas the old one has R initial. Other than that, they look pretty similar. So if I could somehow get mass initial to show up over here and R initial to show up over here, these two formulas would start looking a little more similar. Well, it turns out that the question tells us that the mass has been tripled. In other words, mass final over here is 3 times mass initial. And the question also tells us that the radius is doubled. So R final equals 2 times R initial. Now I can take that and sub it in over here. Instead of mass final, I put 3 times mass initial. And instead of R final, I put 2 times R initial. So now it's starting to look a bit better. I've got a mass initial and an R initial, just like I do over here. What's making this formula look weird is this 3 and this 2. Those are different from what I have on this side. So I'm just going to try and write this a bit differently and pull those 3 and the 2 over to the left, so they're kind of out of the way. And to do that, I'm just going to basically pull them out of the brackets. The brackets on the top, I don't even really need anymore. On the bottom, in order to bring this 2 out of the brackets, I'm going to, rather than leaving my squared outside the brackets, I'm just going to distribute it inside the brackets. So apply the squared to this, and then I won't need the brackets anymore. So if I square that 2, it becomes 4. And then if I square the Ri, it becomes Ri squared. So now, you might notice, I have something that's looking a lot more like what I have on this side. This piece right here is exactly the same as this over here. This is Fg initial. So what this formula tells me is that my new weight is 3/4 times my old weight. So let's just kind of move over to the side here, get a bit more room. So my new weight, Fg final, is 3/4 times my old weight, Fg initial, which is going to be 3/4 times, my old weight was 9,000 newtons. So that gives me 6,750. Again, we know M2, the mass of the Earth, so we could have just plugged that in, but I'm glad we didn't because we never ended up using it. Same with big G. We know what that is. We could have plugged that in, but we never ended up needing it, so I'm glad we didn't. All right. Now let's pull circular motion into the mix and see what we can learn by looking at gravity and circular motion at the same time. Now, I want you to imagine you're throwing a ball. And you're throwing the ball horizontally. You're aiming it horizontally. You're not aiming it up at an angle, or you're not aiming it down towards the ground. You're aiming it horizontally. So let's start with a bit of a picture of that. Here's the ground. Here's you. You've got a ball. You're going to give that ball a toss. And if you throw it, the ball's going to do something like that. And then let's say you throw it a bit harder. You pick it up again, you throw it a bit harder. This time, maybe it does something like that. And then you throw it even harder. And this time the ball goes more like that. Then you think, this isn't good enough, so you put the ball down. You spend a couple months hitting the gym. You bulk up a bit. You come back and you're ready to throw the ball again. And this time you're going to throw it really far. So far that it would go off the screen if we kept the scale the same. So we're going to zoom out a bit. We're going to zoom out so much that we see the entire planet Earth. And on top is you. Holding your ball. And you throw it. And it does kind of the same thing. You aim it horizontally, but Earth's gravity pulls it down and it hits the ground. And then you go grab it and you throw it again a bit harder. And again, it goes horizontally a bit further this time, but it still curves towards the ground and hits Earth. And then you throw it with all your might. And as usual, Earth's gravity pulls it down and it curves towards Earth. But this time you've thrown it just fast enough that the curve the ball has towards Earth matches the curvature of the Earth itself. So the ball is always turning right in this case, always being bent by gravity, always being pulled and turned towards Earth, but it never actually gets any closer. It does a big circle all the way around Earth and ends up right back where you are at the exact same height. This is called orbit. When we put satellites and space stations and spacecraft into orbit around Earth, this is exactly what's happening. We're basically throwing them with a rocket fast enough that even though they're getting pulled towards Earth, they never actually get any closer. Rather than falling towards Earth, they fall around the Earth. So there's a common misconception that if you go up into space in orbit, there's no gravity. That's not the case at all. If there was no gravity, you wouldn't be able to do orbit. If there was no gravity up here and I threw this ball, it would just kind of go in a straight line and never come back. I actually need gravity in order to have orbit. If I want to go in a circle, I need gravity to keep pulling me towards the center. The reason we go up really high if we want to put things in orbit is not because there's less gravity up there. There is a bit less gravity, but not much. If you go up to where the International Space Station is, where astronauts will go and float around inside the space station for 6 months at a time, the strength of gravity up there is only about 10% less. Instead of 9.8, it's like 8.8 or something like that. The reason we go high to put things in orbit is to get out of the atmosphere. If you want to throw something fast enough that it'll actually do this, you need to throw it many, many times the speed of sound. And when you throw things that fast, there's a ton of air resistance, and they will slow down very quickly. So to put something in orbit and have any chance of it staying there, we need to get up high enough that there's no air resistance. That's why we go up high to put things in orbit. It's not to get away from Earth's gravitational field. It's to get away from Earth's atmosphere. So if you are an astronaut on the International Space Station and you're orbiting around the Earth like this, you are always falling towards Earth. You're always accelerating towards the center of the Earth at maybe not 9.8 meters per second squared, but let's say 8.8 meters per second squared. But you're never actually getting any closer. Your acceleration is a centripetal acceleration. So what you're going to do is you're going to feel weightless. It's kind of the same scenario as if you're in an elevator, the top of an elevator shaft to the top of a skyscraper, and suddenly the cable to the elevator breaks, and you and the elevator both start accelerating towards the ground at 9.8 meters per second squared. Inside that elevator, you're going to feel weightless. You can push yourself off of one wall and you'll float to the other wall. You can push yourself off that wall and you'll float back. You can give a little push off the floor with your feet and you'll float up to the ceiling. You can gently push off the ceiling with your hands and you'll float back to the floor. And you can keep doing this, experiencing this weightlessness, experiencing this floating until the elevator eventually hits the ground, and then things get very different. Same thing is happening for astronauts in the space station. The space station is accelerating towards the Earth at, again, let's say 8.8 meters per second squared. The astronaut inside the space station is also accelerating towards the Earth at 8.8 meters per second squared. So as long as the space station and the astronaut remain above the ground, the astronaut is going to feel as if they're floating in the space station. They will feel as if they're weightless because there will be no normal force on them. However, with the elevator scenario, that can only last for so long before the elevator hits the ground. For the space station, because it's in orbit and its acceleration doesn't actually cause it to get any closer to the Earth, it only causes it to keep changing direction. You can maintain that feeling of weightlessness forever. So remember, when you're weightless, you still have weight, right? On the space station, the astronauts have most of their weight still, only about 10% less. What you don't experience when you're weightless, though, is you don't experience the normal force. Your feet aren't on the ground, feeling pressure on your heels, feeling your spine being compressed, noticing that you have to use the muscles in your legs to support yourself. That all happens when you feel a normal force. It doesn't necessarily happen when you feel weight. It doesn't just have to be the normal force, it can be any other contact force, but normal force is the common one. Okay, so now that we kind of understand the concept of orbit, let's see how we can do some calculations with it. A 4,500 kilogram Earth satellite has an orbital radius of 8.5 times 10 to the 7 meters. At what speed does it travel? Okay, so here's our Earth. Here's my satellite. And that satellite has an orbit. It has a path that it is following around Earth. That dotted line is the orbit, and the radius of that orbit is called the orbital radius, as we discussed before. And that orbital radius is 8.5 times 10 to the 7 meters. And this satellite is 4,500 kilograms. We want to know the speed it is traveling at? Well, first of all, this looks a lot like a circular motion problem. So let's set it up the way we would set up pretty much any circular motion problem by starting with Newton's second law, F equals ma. The sum of all the forces is equal to the mass times the acceleration. And so when we look at the thing that's in circular motion, the satellite, we think, okay, what are all the forces acting on it? Well, there's really just one. There's the force of gravity pulling the satellite towards the Earth and pulling the Earth towards the satellite. So when I think of all the forces and I go to list them, I just get one. That satellite feels the force of gravity, and that's it, right? There's still gravity in space. And that acceleration, well, because it's moving in a circle, this acceleration is going to be a centripetal acceleration. So let's see if we can plug in some other formulas now that'll help us with the numbers we actually have. So how are we going to figure out this force of gravity? Well, that's where Newton's universal law of gravitation comes in. Force of gravity can be calculated as m1, m2, big G over r squared. And I actually think I'm just going to write this all a little bit lower down because there's some notes I want to add in here later. And for that acceleration, the centripetal acceleration, there's a couple formulas we can choose from. Because we're trying to find the speed, let's pick a formula for AC that has speed in it. That's going to be v squared over r. So we got a lot of m's here, m1, m2, m. Let's try and get through these. Well, again, if we follow our convention, m1 is the small mass, m2 is the big mass. I think m1 is going to be the satellite, m2 is going to be the Earth. So let's label those as such. This is the satellite. This guy is Earth. Now we've also got this m over here on the other side of the equation. That's my m from F equals ma. So if we think of what F equals ma means, this is the sum of the forces on an object. This is the mass of that object, and this is the acceleration of that object. So what is the object that's doing the acceleration, that's having these forces on it? Well, in this question, it's the satellite. The satellite is the thing moving in a circle, so the satellite is the thing that is accelerating. So the satellite is the thing that we need the mass for. There. So this m is the mass of the satellite. So what that means we could do here, because I've got the satellite's mass over here and the satellite's mass over there, I could cancel them both out. And it turns out I don't actually need the satellite's mass to solve this problem. But I have it. So I think for this example, I'll just plug it in anyways. But note that I wouldn't need to. Okay, so what I'm trying to find here is the speed of this satellite, or v. So if I rearrange this whole thing for v, I get this. And let's plug some numbers in there. M1 is 4,500. M2 is the mass of the Earth. 5.97 times 10 to the 24. You know what? I'm gonna run out of space here, so let's do this a little bit lower down. Big G is 6.67 times 10 to the negative 11. And R is 8.5 times 10 to the 7 meters. R again, 8.5 times 10 to the 7 meters, but that's going to be squared. And M, regular M here, was the mass of the satellite, which is 4,500. So again, I've got some canceling I could have done, right? I've got an R squared down here and an R up top. I've got a massive satellite here and that on the bottom. So I could have canceled some stuff out to save myself some work, but I didn't bother for this question. This is all being square rooted. Since I had all those numbers, I just decided to plug them in. And if you crunch through this, you should get that the speed of the satellite is 2,160 meters per second. So given that the speed of sound is like a little over 300 meters per second, we're looking at like maybe 7 times the speed of sound here. That's fast. That gives you a sense of just how fast you have to throw something so that it never actually, it always accelerates towards the Earth but never actually gets any closer. And as you can imagine, if you threw something at 7 times the speed of sound, there'll be a lot of air resistance to contend with, and that's why you want to be above the Earth's atmosphere. So let's just kind of recap what we did in this question. We had an object that was in orbit. An orbit kind of combines the idea of circular motion with the concept of gravity. So we started out solving this like a circular motion problem with centripetal acceleration. And then we said that the net force, the centripetal force towards the center, was caused by gravity. We used Newton's universal law of gravitation. And then after that, it was just regular circular motion, plug and play, and we got to our answer.